All right, we're recording all of this. So if you have a really good question that you think is like burning desire and you want to be recorded for posterity, let me know. I'll run over and you can talk into the microphone and we'll get you recorded and posted on YouTube. So you can generate your own following, you know. I figure this is my retirement income once I go, that you guys are going to want to watch, because, you know, a lot of people have insomnia, right? And so this is the cure for insomnia. You just listen to about 5 minutes of me and you're gone. You are gone. And I've done research on this over about the last 20 years, and I know it works. It works every Tuesday and Thursday. Okay, wow. Let's see. Okay, so last time we made introductory comments on the statistics of where the power, oh my goodness, you don't have all these handouts, do you? Oh my goodness, come up to the podium. Well, I guess you might want one of those. That's not mine. I don't know what that is. That's some garbage. Take one of those. One of those. Take one of those. I'll take one of those. You already have one of those. One of those. One of those. Let's see. I think that's good, and you need to sign in on that. Okay. So, young man that just came in, I'm sorry, I don't know. You're going to need to come up here and get handouts that you don't have. I think some of these we did last time. You probably have. Were you here last time?
Yeah.
Okay. Okay. And you got that one. I think you don't have this one. I'm pretty sure you don't have it. You don't have this one. You don't have this one, and you probably don't have this one. Okay. Very good. Thank you. Okay. So we talked through the stats a little bit on where power came from, just to kind of get a feel. Let's see. You had an article, and you owe me write-ups today. And if you don't have it today, you can turn it in later. So that's not a problem. And I will get those out. We have a new article today, and we're going to have a quiz on that. Transformative coal-powered technologies take shape. I'm going to give you a 10 to 20 question little true-false multiple choice test over this. I just want to assure that you read it at the start of class next time. What are you doing?
I don't think everybody got that. Oh, can I just pass this one around? I didn't get it first.
Well, all of this will be available to you after class. What we may do is like lay it out on the floor, and you can shop around and make sure that you have the handouts. I will do my best to email it out. I think I emailed out all of the first ones, but I haven't emailed out the ones for today. But just read this. It's not terribly heavy reading, but if I don't give a quiz on it, you won't read it. I've been around long enough to know that. So anyway, let's see. And then we started talking about electric rate structures last time. And I think we, let's see, which one is this? This is this GSA? No, this is TD. Let's see, we started with the GSA rate. These are Nashville rates. These are current. And I want you to understand how electricity gets sold. That's part of it. And I'll just hit this again real quick. If you have questions, you can come by and catch me after class or tomorrow, and or sometime. I should be around all day tomorrow. We'll go to GSA 3. There's actually 3 rates here: GSA 1, GSA 2, GSA 3. As you go down, it's for larger customers. GSA 3 is for demand of 1,000 kW or more. That would be, typically it's like a contract demand or a billing demand. And we made the distinction last time that when electricity is sold, there's actually two main parameters. There's the energy, electrical energy, which is kilowatt hours. And then there's demand, which is like the instantaneous rate at which you have the maximum instantaneous rate that you have used power over the billing period. And the meter keeps up with that. But it's not exactly instantaneous. It's typically a 30-minute, it could be a 15-minute or a 30-minute average to kind of level out any big spikes that may come instantaneously when equipment starts. But so as we go through this, you'll see there's a demand-based charge, which is kW, because that's rate-based, and there's an energy-based charge, which is kWh, which is electrical energy. And they do all sorts of permutation. There's lots of different rate structures. There's time of day rates where the rates change during the day. There's simpler rates where it's more, you know, just a flat multiplier times an amount, as we'll see. And so this is a little bit of a review here. But for GSA 3, this is the eligibility. There's probably some more stuff further up about eligibility in here. But anyway, so if you're on this rate, you're going to pay $934.50 per delivery point, per metering point per month for the privilege of being their customer. Then TVA is going to put a grid access charge on you of $205.30 per month. If the customer's average monthly energy, kWh, for the last 12 months is not more than 150,000. Well, if you do a little arithmetic, you're going to realize that if your demand is north of 1,000 kW, you're most likely going to be more than this. And so, but it depends on your billing for that month. But most likely you're going to be in this bin down here. So you're going to pay, instead of the 205, you're going to pay $579.04 a month for the privilege of purchasing power from Tennessee Valley Authority. They thank you very much. Okay, so then the demand charge. Okay, so there's a little algorithm here. They will determine your billing demand for the month. So for the first 1,000 kW, and you know, we can make up a number. Let's say we have to pay for 1,500 kW. So they're going to charge you for the first 1,000. They're going to charge you $19.80 per kW for a cool $19,800 cha-ching on your bill. Jared, thank you very much. We appreciate your business. And then for that extra 500 kW, it's going to be $19.93. So whatever 500 times $19.93 is, they're going to add that to your bill. Thank you very much, Mr. Dill. We appreciate your patronage. Okay, and then if something unusual happens, let's see, this is for any kW, each kW, if any of the amount by which the customer's billing demand exceeds 2,500. So see, they're really not wanting you to get way up there in this rate structure, or a contract demand. So if you're going to have a contract demand above this, you probably wouldn't want to be on this rate structure. You probably would find another one that worked out a little bit better for you. Okay, so that's in the winter, or that's in the summer. The winter period, it's the same algorithm. They just changed the numbers a little bit. And then in the transition months. So the summer, if you go down here a little bit, it will tell you determination, seasonal periods. There you go. June, July, August, September would be summer. December, January, February, March would be winter, and all others, the swing months, would be transition months. Okay? So that's how they're going to charge you based on your billing demand. Then we have this, let's get down here. Here's your energy charge, which on this rate structure is actually pretty simple. Okay? So for the first 150,000 kilowatt hours, you're going to pay 6.1 what's that? 147 cents per kilowatt hour. So straight multiplication. If it's more than, let's say if it's, well, let me see, did I bring my calculator? We said 1,500 for demand. So for a peak is 1,500, something like that. In a month, there's 730 hours in an average month, times 730, times a load factor, say 0.7. So let's say it's 750,000 kilowatt hours would be typical for a 1,500 kW demand. So we'd take this 1,500, or 150,000 rather, times 0.06147, and that's $9,220.50. And then all the rest of them, so I said, what, 750, what is that, minus 150, that's going to be what, 600? 600,000 times 0.05327. So that's 31,962 plus recall 1, add them together. It's about almost 42,000 for the energy. Okay, so cha-ching, you get to pay that too. They're into this paying stuff, you know. That's why, you know, sometimes, you know, big companies, they gotta raise prices. Power cost goes up. They got to pay this every month, you know. Okay, and then they'll put tax on it. Should be 1.5%. Sometimes there's facility rental charges. I'll show you a real bill in a second that came in. We visited the old Federal Mogul plant up in Sevierville last week, and I've got a detailed breakdown of one of their bills. But I want to show you this one other rate structure before I do. And we need to talk a little bit about this power factor stuff. Okay, determination of demand. So the meter records the highest kW, 30-minute average, during this whole 730-hour month. They get a number, 1,500. They say, well, that's good. We'll charge you for at least 1,500, but let's see if we can do some magic on this and we can make a little more money out of it. Okay, so that's what they're going through here. So the distributor shall meter the demands in kW for all customers. So they got to invest. They got to probably spend a couple $1,000s for this nice meter, and they hang it on the wall. And they can read them remotely these days. They just punch into your account whatever meter reading date, and shazam, oh, 1,500 kW. All right, we got some cash there. But they're going to go through this further little procedure here. The meter demand for any month shall be the highest average during a 30, so this tells you it's a 30-minute window, 30 consecutive minute period of the month, of the load metered in kW. The measured demand for any month shall be the higher of the highest average during, or so here they're going to try to adjust it upward. So your billing demand, they'll go through this A and B here, and whichever produces the largest number is what they will charge you for, okay? Because just because the meter says 1,500, maybe they can squeeze this up to 1,600 and make a little extra cash on you. You know, hey, they're not opposed to that, trust me. Okay, so it would be A, the load metered in kW, what the meter says, or this is where the weasel words come in, 85% of the load in kVA plus an additional 10% of that part of the load over 5,000 kVA. And such measured demand shall be used as billing demand. So whichever one of those is larger is what they're going to bill you for. Okay. Now this gets us into this power factor discussion. And so you have a presentation. I guess we should just go ahead and do that. It's about, I don't know, 12 or 13 or 14 slides here. So we need to go through this. This is all that crap they probably talked to you about in your ECE class that you really didn't want to learn. and you thought you had avoided, but no, you haven't. It's come back to find you again. Now, I don't know if they even cover this. It's not too bad. All right, so first of all, let's go through a little bit of just harangue here. Why do we care? Why would Spencer, you owned your own business. If you own that Federal Mogul plant, that Federal Mogul plant made 57 million valves for cars last year. And the sales were like, it's 56, they're about $1. They're about $1 a piece. Man, there could be some money in that. What if you could make them for a quarter? Woo! Spencer, you would have sold the plant by now, and you would be lounging at Mar-a-Lago at the President's Resort, right? We don't want to get political. I'm just joking. All right. So anyway, you care because this could affect your retirement plans. You know, because you want to glean every penny of profit possible out of that plant, and I don't blame you. That's the American way. Okay. Well, why do we care about low power factor? Well, we get into the engineering of it a little bit here, but as power factor drops, the current flow required by the electrical system increases. Now, the power doesn't necessarily increase, but the current draw increases. And that current draw is current that the power company cannot sell to another customer. So you are reducing their opportunity to make money off of their generation by screwing up your power factor. And we're going to get you for it. Okay. Higher current flows, and it also, if you put more current through a wire, you have more resistive loss, I squared R. Whatever the resistivity of the wire is, current squared times resistivity in correct units will give you power loss for just flowing the current through the wire. So power factor goes down, current goes up, I squared R losses have to go up proportionately. This is the big reason, causes penalty charges on your electrical bill. And you don't want to pay penalty charges. Power factor is a measure of your electrical system efficiency in handling power, and the more current you put through there, the more voltage drop you'll have. And so lower voltage then requires an additional current because the voltage went down, okay, for a given kW draw. So all of these things are negatives. But the bottom line is it can cost a business money. Okay, so let's get into, just a simple equation. This is, we wrote this up there last time, but I know I scribbled up and it wasn't very pretty. And so, I'll give you something you can read. So kW, that's a rate of using energy, Newton meter per second, is volts. And we said last time, this is really the RMS, the root mean square. If you look on an oscilloscope, these voltages jump up and down. It's a sinusoid, right? But this is what they call the RMS value. It's really, if you put a meter on there, it reads RMS. It tells you it's 462 volts. That's an RMS voltage, okay? Same thing on amps. That's an RMS amps. PF is this power factor, and this would be a decimal number between 0 and 1, okay? 1 being perfect, 0 being not so good, like being probably not possible all the way down to 0. Three-phase is for, the square root of 3 is for three-phase circuits, which circuit of any size is going to be three-phase. My little stuff I plug in my office is single-phase. If it's single-phase, you just drop the 3, square root of 3 out of it. And then all of this from here back would produce watts. And so we just divide by 1,000 to get it in kW. Okay, so because, the number's too big. If it's really big, we divide it by 1,000,000 and get megawatts. But for this discussion, and your utility bill usually comes in terms of kW, okay? So for a purely resistive load, like that little chill chaser I keep in my office plugged in, that little resistance heater, power factor's 1. Perfect, straight up and down. So no power factor issue with that. It's 1 for purely resistive loads, less than 1 for inductive loads. Well, what's an inductor? That's some sort of an iron core with a wire wrapped around it. And we have these things called induction motors. And you could probably figure out an induction motor is going to have some inductance, and that's going to cause a shift in power factor, as we'll see. So, and there's other devices that we'll see. Yeah, I mentioned induction transformers, induction furnaces. The old lighting ballast, not the new electronic, not so much, but the old lighting ballast were just transformers. So they did, but those things have pretty much gone away. I probably should take this out. This shows just some pictures of resistive. That's a resistive heater, or just an incandescent light bulb. That's just a resistance element. There's no induction. So those things would have a power factor of 1. But when you get to anything with an iron core, a coil in it, induction motor, induction furnace, something like that, they're going to have a power factor of less than 1. And we'll talk a little more about what happens with all that. In power electronic devices, if you monitor like a computer power supply, oh, they've got really chopped up waveforms. They're chopping this and doing that and the other, and I mean they have power factors less than 1 as well. Usually, for most industrial type settings, those types of devices, the load on those is pretty small. Now, if you had a big data center or something like that, then that would probably be the main source of a bad power factor. But for most, computers, if you got a big plant out there, the computer load is nothing compared to the rest of the equipment, the motors and all the other stuff in the plant. But I've got a bigger presentation of this where I show some waveforms, but there are some pretty funky waveforms come out of some of these power electronic devices. Okay, so to correct that kind of stuff, you need electronic filtration, which is beyond the scope of what we're doing here. We're not going to get into that. Oh, well, there's a picture. Yeah, that's on a computer supply. That's pretty funky. The voltage is nice, but the current, look at that. That's pretty screwed up looking. Anyway, so some plants have a big issue with this and some don't. This is cut and pasted from some DOE literature. Sawmills are pretty bad. A lot of these types of plants tend to have low power factors. Okay. This shows, say, a sawmill is a good example. A lot of this type equipment, what happens is stuff like these motors, these saw motors and chippers and stuff like that, on a big saw and a sawmill, they don't start and stop it. It's this big saw. They just start it and it runs all day long. And it occasionally cuts a board. It's sitting there, a log comes along and zzz, 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 and then it sits there waiting for the next log. And then zzz, zzz. So it spends a lot of time running unloaded. Unloaded motors are a major contributor to this. Oops. There we go. And that's what this shows. So we've got some different curves here that represents different size motors. So up here at the top, these are big guys, 200, 250 horsepower. And this little dotted line you can't hardly see, that's 5 to 10 horsepower. And this is like percent full load amps, or this is load on the motor. So over here at 100%, this 200 horse motor is actually putting out 200 horse. This 5 horsepower motor is actually putting out 5 horse, 10, it's fully loaded, okay? But most motors run, are sized a little bit bigger than the load. I mean, if I'm buying a motor for a pump, if I figure the maximum horsepower that pump's going to need is 28, I'm going to put a 30 or 40 horse motor on it to make sure I don't overload the motor. And so then when they turn it on, maybe it actually needs 22. So then it's running, I got a 30 horse motor or a 40 horse motor actually pulling 22 horsepower. it's pretty much, it's only about 50–60% loaded, which puts you back in, there's 50% load, there's 75% load. So you see, as the load goes down, we see the power factor fall off, okay? And the other thing to note is that big motors have better power factors in general than small motors. So this big guy up here, this is what, 85–86%, something like that. The best this little guy can do is down here about 70%. That also has an impact. If I have a plant full of small motors, even if they're loaded, they're going to have a crappy power factor. So it's the kind of like the summation of all of that at the meter is that's what the meter sees. The summation of all that stuff that's going on in the plant behind it affects the power factor that the meter sees. Okay, so you got a whole bunch of this going on. So it contributes to an overall, that's kind of the same thing. I'm not going to, my clicker is blocked. Technical difficulty here. Oops. All right. There we go. This just shows a, is this the, I thought this was this may be the big presentation. I may have opened.
I think we don't have all the stuff.
Okay, you need to tell me that. I opened the wrong presentation. This is the full size presentation. This one's, this one's got 71 slides. I'm sorry. I have culled this down. If there's a way to foul it up, I'll find it. 4610. Let's see, 46. Brief. There we go. Let's see. I was going to say. All right, so we talked about that one. Oh, we're done. Okay, so if power factor is 1, kW is equal to kVA and we'll show the equation in a second. The equation for power factor is kW divided by kVA. So if kW divided by kVA is 1, kW equals kVA. And there you go. Okay, so this is the power triangle. This is kind of where the rubber meets the road. You can pretty well understand this, I think. So what you see is this top side of this triangle represents real power, kW. That's what the meter is recording, kW. Volts, amps, power factor, 1.73 square root of 3 divided by 1,000. Okay, the hypotenuse is what we call apparent power, and that's volts, amps, square root of 3 without power factor. So if you solve for power factor, then in terms of this, it's got to be what, kW over kVA, which is the cosine of theta, which is the power factor angle. So this is, for as far as doing math, we're doing Pythagoras' theorem or a little basic trig. So it's not too bad. The sine side of this vertical side over here is what we call reactive power, which is kVAR. Okay. So as the power factor gets worse, what happens is this reactive power side gets longer and longer, which makes the hypotenuse get longer and longer, but the kW side doesn't change. And so when this side gets longer, the only way the hypotenuse can get longer, the voltage is constant at whatever it is. Square root of 3 is constant, 1,000 is constant. So it's the amps that have to go up. Okay. So that's kind of the effect. So with inductive loads, that reactive power, kVAR, is required. And what that is, that's energy that goes into establishing magnetic fields that are in the iron core and around the conductors. Okay? And when that happens, it causes a shift in phase between the current and voltage. I've got some pictures here. And the more of those phases, the more those two waves are shifted out of phase, the lower the power factor and the more the current gets driven up. So this shows a purely resistive load. This is perfect. And notice everything peaks together. So what have I got? The red is voltage, the blue is current, and the golden eagle purple is power. Okay, so see, we're crossing, we have our positive peak at the same point. We have our zero crossing at the same point. We have our negative peak at the same point. Of course, power is always positive because if these two are negative, or at least on this one, if these two are negative, then it flips it up. But so that's what you want. That's power factor 1. And so that's kind of what we strive for. That's the most efficient way to utilize that electricity. However, in a circuit with a bunch of inductance, what's happened? The current is lagging behind the voltage. So see, the voltage peaks over here, but the current doesn't peak till later. And so the voltage crosses zero here, but the current crosses zero here. So this is a phase shift. And that, in angular terms, that's theta. The power factor angle is the phase shift between those two. Well, so this is the problem. So the inductance, that energy feeding in, that magnetizing energy, but it feeds in a positive sense. But then as this wave starts to collapse, that energy goes back into the circuit and it retards the current waveform. That's what's happening. I mean, if you want to get into the physics of it, and that's what causes this effect. Okay, and this has some real practical ramifications for us. So in order to see what happens, I've made up a little example here. So let's say just that we have a simple 100 kW load. And it's going to be a 100 kW load in both cases. But for number one, it's going to be an electric resistance heater, just a strip heater, okay, that's pulling 100 kW. In case two, it's going to be a lightly loaded 250 horsepower motor that's actually putting out 127 horsepower. And that translates into 100 kW of input power to the motor. So let's see what happens. So case one, well, there is no reactive power, so the power triangle collapses to just two lines. This is the kW and the kVA, and they're both 100, and they're laying right on top of each other. That's my kind of triangle, right? Pretty simple. Two straight lines on top of each other. Okay? So let's do the math. So, I made up a voltage. I said, let's just say the voltage is 230. Let it be whatever you want it to. Just keep it constant. And so 100 kW, 230 volts. And of course, I went ahead and calculated the amps and stuck it in here. So this requires 251.3 amps, power factor 1. It's a resistance load, square root of 3, divided by 1,000. Power triangle, two lines on top of each other. Parent power 100 kVA, metered power 100 kW, three phase 230, 251.3 amps. It doesn't get any better than that. In the world of Sparkyism. Okay. Number two, still 100 kW, but now, oh my goodness, this induction motor has a pretty bad power factor of 0.7042. I don't know how I came up with that, but anyway, I don't remember. It's been too long. But anyway, I mean, it can be whatever it is for the example. At 0.7042, that requires 356.9 amps. Oh my, look what happened to the current. It's still 100 kW. The power meter on the building is going to read the same, but now you're sucking up another 105.6 amps. And the power company goes, hold on. I wanted to sell that to this guy next door, and you're taking it. They say, oh, you're going to take that much, I'm going to penalize you. That's why that's what's wrong here, okay? And, you know, what causes this is typically all those motors that you have, either a whole bunch of small motors. You may have a plant full of 5 and 10 horsepower motors doing Lord knows what. Conveyors, conveyor, like a I bet FedEx, if they didn't correct it, they would have a horrible power factor because they got all these conveyors, and a conveyor is not a big motor, maybe 10, maybe at most 20 horse on most of them. You know, it's just pulling, just all day long, pulling conveyors along. So they're going to get dinged on this if they don't put on some capacitors and correct it. So look at the reactive power. And you get this from, usually the bill will tell you the power. If you're doing a whole plant, the bill will tell you the power factor. Or I've got a 3-phase power meter. I can clip on a motor, and that meter will tell me what the power factor is on the motor. I just measure it if I want it on a particular load. Or I can, you can put your meter next to the plant meter, or you can tie into the utility and see what they see. And you go, oh my God, they're going to kill me this month. You can see it coming. Okay, so this additional 105.6 amps of current that occur because of the inductive load, it doesn't change the kW reading on the meter, except that additional amps will have some I²R loss. I can't put another 105.6 amps through a wire and not have some additional losses. So that's a small loss. That's usually 1% or 2. That's not huge, but it's there. Causes the utility to provide this extra current. And the other thing that happens, you see, in a plant is sometimes, their distribution system will be maximized. Like they've got what they call an MCC, a motor control center, that all the power flows through to this part of the plant. And they want to add another motor. They want to add another load. And the electrical guy comes in and says, hey man, that thing's pulling 429 amps and it's rated for 440, and you can't put another load on there. Well, but you can go to those existing loads that are fed through there, and if you can correct some power factors at the motor, you can put the capacitors directly on the motor, and it'll correct it there, and it'll reduce that current flow through that MCC. That can be a huge savings for a plant, because maybe they just want to add a 50-horse motor. They need to add another pump down here, but they got to feed it. The MCC is loaded, so they correct power factor on 3 or 4 different motors to serve through that MCC. That reduces the current, and then they can add another motor, and they don't have to do a project to expand the electrical system, which is horrendously expensive. You got to add another MCC, you're probably talking $200,000. You could add a 50 horsepower pump for maybe $10,000 or $15,000. So see, there's lots of reasons why a plant might want to do this. But anyway. So reasons: avoid penalty charges, reduce current flows in the electrical system, reduce I²R, possibly unload circuits, transformers, so you can add additional loads. Okay, that wasn't just so painful, was it?
When you say put a capacitor on it, can you describe that in more detail?
Can you do what now? Say that again.
When you say put a capacitor on it,
yeah.
What do you mean by that again?
Well, it's like the larger presentation goes into this. What happens in a capacitor basically stores electrons and then discharges them back into the circuit. So that action basically will retard the voltage waveform relative to the current. So you've already, with the low power factor, you've got the voltage peaking first and then the current. But if you add the right amount of capacitors, you can slow that voltage waveform down and put it more back in phase with the current. And so that's why you want to do that. And so you get the current reduction from the point of capacitor application back to the power plant. Now, so, and it's hard for my little brain to understand why this is true, but it is. If you put your capacitors on at your meter, which will save you your billing, you know, it will get you out of penalty. The current downstream is still high, but the current at the meter is low. Don't ask me why, Jared. I see that look on your face. And we're going to have to go. Oh, my gosh. I've asked the double E's this before. I don't know. They've got some explanation.
So that would be the cost-effective measure, is to put capacitors right before they measure your electricity. And it would.
That's what people usually do. Well, I mean, a lot of people, though, do correct it at the MCC. It's either at the MCC or one big bank at the meter. But if you do it at the meter, it doesn't unload the circuits out in the plant. It just unloads it from the point of capacity. So if the power company's here, power plant's here, your meter's here, you put them right here, and you get the unloading from the capacitor back to the plant. But that doesn't help you out here in the plant where you still have circuits that are loaded. So it depends on what's your purpose in installing the capacitor. Is it just to avoid penalty, which is typically the cost? But it doesn't have to be. It could be a combination of these things. So you got to figure out where you want to put them. And you know, you're going to hire, there are companies that do this. TVA will come in and do a study for a business and tell them, give them a recommendation and meter all this stuff for you. They'll do it for nothing, you know, but anyway. Anyway, I mean, I just want you guys to know this stuff is out there and, you know, have some appreciation for it and how it affects the bill. You know, because that's really what ties into the steam power plants. This is the marketing side of electricity. Okay, so now we want to go back. Oh my gosh. How am I going to find the right one? Oh, we'll find it. Okay, so this is where we were. Okay. So this 85%, so 85% is the threshold for penalty. So what they're doing in that calculation is they're saying, okay, here's the power triangle. Okay, and so this is kVA, this is kVAR, and this is kW. Okay, and so power factor is equal to kVA. Well, okay, if 85% is my threshold, what I'm going to do, because see, this number is constant, is really independent of power factor, right? This is the actual power that is used by the load. This is the number that goes up as power factor goes down. They say, okay, this is the number I'm concerned about being too big, so I'll take 85% of this and compare it to this. So that's what they're doing. They're saying, okay, well, if your power factor is above 85% and I take 85% of this, it'll be less than this. But if your power factor is less than, let's say your power factor is 0.6, I take 85% of this, I'm going to get a much bigger number than this. And they say, fine, I'll just charge you for the big one. And that's what they're doing. So that's what that calculation is. So they're either going to charge you for the meter demand or they're going to charge you for 85% of the load in kVA. And then plus they've got this extra 10% if you're drastically too large, but that usually doesn't come into effect. You don't see those very often, but I mean, they will do that calculation. But if you're on this rate structure, you're probably not going to be above 5,000 kVA. All right. Questions? Okay. So now here's the time of day. So let's look at, yeah, this will just be one. One is just one until, well, we'll go to 3. Let me see, is that right? Is this the time of day stuff, winter? Nah, this isn't the one I want. What is this? Time of day, let's go to this one. I'm sorry. I'll get here in a second. Whoops, did that wrong. There we go.
It's right above the termination of, termination of on-peak and off-peak energy route.
Okay. Yeah, okay, this has the on-peak, off-peak. Okay, facility rental, reactive, and this one does reactive charges in a different, okay, but so now we're going to have, in each month, we're going to have on-peak hours, which are more expensive, and we're going to have off-peak hours, which are cheaper. And so this determination of on-peak and off-peak hours, because we went through some of this the other day, but let's see, so for the summer, the on-peak is 1 p.m. to 7 p.m. And in the winter, when it's cold outside, it's going to be, yeah, this is January, February, March, November, and December, 4 a.m. to 10 a.m. Okay, so the meter keeps up with all that. So we can look at this. Base charge, $2,000. Administrative charge, $350. Demand charges. Summer on peak, $10.24 per kW. And say the meter keeps up with 2 different demands. There's your peak demand during the on-peak hours of that month, and there's your peak demand during your off-peak hours. And there are 2 completely separate entities. It also keeps up with energy. The energy used on peak and the energy used off peak, and then the total energy would be just the sum of those. Okay. So in the summer, you're going to pay $10.24 per kW for each on-peak, for your on-peak demand. Plus, they're going to look at your on-peak and off-peak demand, and they're going to pick the big one, and they're going to charge you another $6.38 for the bigger of the 2. So, you know, if they were equal, you would just be paying the same number. You'd be paying, what, $16.62 per kW. But so they're gonna this maximum, they're gonna ding you on whichever one's biggest. And then excess, if you go over by which whether the billing demand exceeds its on-peak contract or the customer's off-peak billing demand. So if you're exceeding contract, which that does, I very rarely see people exceed contract. I don't know that I've ever seen anybody exceed contract. So that's pretty rare, at least in my estimation. Winter, same structure, different numbers a little bit. And then the transition and the winter are the same. So, you know, they're not jacking it too much. So that's demand. Energy is really a hodgepodge. This is the one that confuses everybody. If you're not already confused, this one will get you, I promise. So now the on-peak is simple. It's just however many kilowatt hours you use during that on-peak period times 7.44 cents. That's pretty simple. We can do that. Okay, the off-peak is this stupid block thing, and we mentioned this last time. I don't know why. Why in the world somebody came up with this? I have no idea. So, I mean, they're telling you what they're doing right here, but it takes, so there's 200 hours. What they do is 200 hours of the on-peak demand. Okay, so they're going to take, now this is off-peak energy, but they're going to take on the peak demand, and that'll be kW, times 200 hours. You know, that's some, well, I guess we should, yeah. Anyway, so that's some number, let's just, I don't know, let's say that's 200,000 kilowatt hours. So I guess that would make this 1,000 then, wouldn't it? Is that right? 1, 2, 3, 4, 5, 3, yeah, okay. So if this was 1,000, this first block would turn out to be 200,000 kilowatt hours. Well, no, not completely. We're not done yet, I'm sorry. But then you have to multiply that by the ratio of the off-peak energy to the total energy. So we're not, that's not finished yet, sorry. Lost my head. Times off-peak kWh divided by total. There you go. And that would be the block size. So whatever that came out to be, we could say, you know, maybe it's 3/4, so I don't know. What's that? 3/4 would be what, 150? Let's say that comes out 150,000. So this would be block number 1, okay? And so for all of those, so long as you used that many, which, trust me, you did, that's times 4.94 cents per kilowatt hour, okay? But that's not your whole bill because you've used more than that off peak. So now you go down to block 2. Well, the calculation of the block size is the same. So block 2, so this would be number 1. Number 2, it's the same math. So it's going to result in 150,000 kWh. Now, you have to be mindful that you paid for 150 here, you're about to pay for another 150 there. You got to make sure that you used more than 300 or you don't have to pay for all of that second block. You just have to pay for what you used of it, okay? But, you know, on an account like this, you're probably up close to $1 million or something, or 700,000 or something like that. So you got plenty to pay for, okay? So long as you've saturated both blocks, then this second block charge would be the 150,000 times 2.197 cents per kilowatt hour, okay? Then at that point, you would have paid for 300,000, yeah. Well, yeah, because look, it's the same. Oh, no, no, it says, you know, you just do what it says. Yeah, yeah. Yeah, I mean, you can think about it that way. Okay. So then the third block, say in excess over 400. So then all of the rest that you haven't already paid for, you pay 1.942.
So it's really like a break, right? I mean,
yeah. Well, okay. So you go in a plant or something looking to reduce cost. If you can switch, look, if you can switch energy use from this period, say you're already in the third block, you can go from here down to here. Well, what kind of savings is that? It's pretty nice savings. But you got to say, Mildred, would you mind working the late shift? You know, we could, you know, you run that machine and that machine makes these, you know, finishes up the widgets. And we could do that from 10 o'clock at night until you know, 4 o'clock in the morning, are you willing to come in? And Mildred says, hell no. I'm quitting. And the problem is Mildred's the only one in the county that knows how to run the machine. And so it's not always easy to do. Sometimes you might save $5,000 a year on energy, but the new guy is going to trash $20,000 worth of parts, and you go, we better just keep Mildred during the day. You know what I'm saying? So, you know, but the bean counters are, you know, and the energy managers are out there. I mean, I go in plants all the time. I say, and sometimes it's much more marked than this. Sometimes there's different rate, the bigger rate structures. You get down to that third block. I mean, it's like a tenth of a cent. It's like a tenth of a. I mean, it's freaking free. The question is, what do we got that we can move from on peak to off peak that's not going to screw up the operation? You can't shut down the plant. I mean, you know. So, but the smart guys are out there at least thinking about this. Says, hey man, you know, if we can shift this operation from first shift to second shift, it'll reduce the demand. You know, look at the KW. What if you can shift? Let's see. So in the summer, what you could say, instead of, if you can shift KW from here down to here, well, that's $3.50 or something a KW. Over the course of a year, if you can shift 200 KW, that's money in your pocket. Absolutely. So, and that's why the utilities do this. They want you to level their load. Because see, when that rate is high, that's when everybody's using electricity. So it helps them to shave that peak and put it down here in the valley where nobody's using any. And this is how they give you encouragement to do that. If you're going to you can use all you want on peak, and baby, we're going to zing you for it. You're going to play ball with us, move it off peak, hey, we'll save you some money. It's up to you. Okay. That's pretty good. How are we doing here? We got 20 minutes. Let me see. Is there anything else we need to do in here? Facilities rental. Okay, so, this has to do with the transformers. Who owns the transformer? Distributor. They'll let you own your own transformer. You own your transformer, you do maintenance on your transformer. Big transformer goes out, that's not good. Main transformer supplying the whole plant goes down. That's not good. Does the plant want responsibility for the transformer? It's a call. They could probably save some money, but you know, that transformer, it's going to go down on the coldest night of the year, you know. I mean, Murphy's always lurking, right? And so, you know, what's going to happen? You know, do you want to call up the utility company and have them scramble their troops? Or do you want to scramble your troops on Christmas Eve? It's your call. But here's some of the information. There shall be no facilities rental charge under this rate structure for delivery at bulk transmission levels of 161,000 volts or higher. Yeah, that's what I want to do. I want to own a transformer that's receiving power at 161,000 volts or higher. I'm only part of that. And neither does the customers. Now, you know, Eastman maybe. Eastman may have, you know, qualified power engineers. You know, they're big enough. I mean, that's a city. They may have a power group that can handle that. They can save some money probably by doing it. It'd be interesting to know. Most plants aren't going to touch that with a 20-foot pole. For delivery at less than 161, there shall be added to the customer's bill a facilities rental charge. This charge shall be 36 cents per kW per month, except for delivery at voltages below 46,000 volts, in which case the charge will be 93 cents per kW per month. For the first 10,000 kW, and 73 cents per kW per month for the excess over 10,000 kW. Such charge shall be applied to the higher. Now they got to figure out, okay, that's the rate. Now how are we going to determine the kW that we plug in here? That will be the highest billing demand established during the latest 12-month consecutive period. That's called a ratchet. Every time they get a new one, they look at the past 11. So they got 12. And for this charge, they go, oh, this one was bigger back here. I think I'll use that. Thank you very much. That's the ratchet. That's number one. Or the customer's currently effective on-peak or off-peak contract demand. Oh, well, see, like I said, you rarely, if ever, see people actually exceeding their contract demand because there's penalties in that. This is, but so let's say your contract is 5,000, but you actually pulled 5,200 1 month, 2 months ago. So they say, well, forget the contract. They're going to find the biggest one. If the contract's 52 and 50 and you bill 52, they're going to remember 52. You're going to get to pay for that 12 times, that extra 200. Welcome to the real world. And the plant manager has to explain that to corporate. What happened to your damn utility bill? You're over budget. Well, Pete left everything running and dadgummit. Whatever happened. There you go. So, in addition to other charges, blah, 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 blah. So anyway, that's pretty good. Okay, so next time I'll make up a little, oh, I know what I was going to do. I was going to show you some actual stuff here. I got this new computer and I don't operate it very well yet. I'm getting better. Not much different, but it's a little different. Tenneco bought Federal Mogul. Well, that's not here. Here's the spreadsheet. I'll have to go find that. Oh, I know. One little thing. Okay, so there's their demand. So what do we see? We're seeing on-peak metered, on-peak billing. Okay, in this rate structure, I think anyway, this rate structure, they don't boost the kW for penalty. They calculate a reactive demand charge based on how far over the allowable kVAR they are. So this rate structure is 95%. Okay, so that we'll take a month up here and play with it for a minute. Let's see. So if I take this 3938. 38, okay? And the penalty is, or the threshold is 95% power factor, okay? So let's just play with that a minute. So this was the meter demand. So what's the allowable kVA in order to be just at the penalty threshold? Well, you take this divided by 0.95, right? Because power factor is this side divided by this side. So if it's 3938 divided by 0.95, that's 4145.3. So this side could be 4145.3 kVA at the threshold 95%. Now they're below that. So theirs is going to be down here someplace. And we'll figure all that out. So store 1. Okay, so what's the allowable kVAR? So the allowable kVAR is this side of this triangle when this is the kW and this is the kVA. So this squared minus this squared square root is this side, this Pythagoras. So what is that? That's recall 1 squared minus 3938 squared equals square root. It's 1294.4. 1294.4. So is allowable. Okay, and so under this rate structure, they're going to charge them $1.46 for every kVAR that they exceed this number. Okay? Let's see. Well, this is the excess. So what the utility does is it calculates that number I just did, and it looks at what their total kVAR is, and it subtracts that from the total, and this is the amount that they exceeded that number by. Okay, so here, let me. So their actual triangle is more down like this. Okay, and so this piece right here is the excess, and what is that? That's 1552. That's 1552. So that plus 1552. So their total kVAR was 2846. So this whole side here .2. Okay? And so what the utility has done is they calculate how much they're in penalty, and it's $1.46, like I said. Store 3. So that's what is it? 1552. Did I write that up there? Yeah, 1552 times 1.46 is 2266. 2266. And they do that every month. $29,351. Thank you very much. That's what you get for exceeding your power factor penalty threshold. I'd say that the bigger the rate, the higher the better the power factor has to be. On the smaller rates, like that GSA 3, it was 85%. This is a bigger rate. This is a bigger customer, and they're holding them to 95% threshold. There are places in the country that it's 97. And, okay, if you overcorrect, you can go from lagging to leading power factor. You can push the voltage past the current. You get to pay a penalty for that too. It's $1.10, I believe. We can look at the bottom of the rate structure, but I believe it. Now they don't charge you as much because leading helps the utility because almost everybody's lagging, but they're going to penalize you anyway because they like your money. So you got to correct it, but you got to correct it the right amount. So when you put in these capacitors, you have to do a study where you monitor this over time and you see how it jumps around because, you know, during operation, you start and stop and stuff all day long and it jumps up and down. And so what you do, you calculate, well, the most capacitors I would need is this, but I need to be able to switch it. Say maybe I'm going to put in 2000 kVAR, but I'm going to put in a switching bank. And the controls on the capacitors monitor the power factor, and maybe you're switching, 300 kVAR blocks in and out of the circuit all the time to keep you from going too far. Because if you put all 2000 in all the time, you'll drive it into lagging most of the time, or half the time. So that's part of the project. You have to monitor, you have to see what the distribution is, and so you put in controls to switch that. And of course, the more controls, the more switching, the more blocks, the more expensive the project is. TVA did, I have a study. TVA did a study for this plant, and I have that. Okay, power factor analysis for Federal Mogul. July 24 of 19. So this is pretty current. That's just their letter, blah, blah, blah. Site visit. Introduction, I don't know. To analyze the cost, site visits. So these are their, what's this? They're different transformers, different circuits, KVA rating. Say, there's their rate, time of day, manufacturing service agreement, 95%, 30-minute demand, power factor. There's your $1.40. Oh, it's a $1.14. I'm sorry, I remembered it $1.10 for leading. There you go. Slightly different period. During this period, it was 28,000. And they project 90K here to fix it. Harmonic. There's some more electrical. You can get into harmonic oscillations and this stuff. Current distortion limits. I don't know. This may be more than this is beyond. But anyway, this is their discussion of power factor. There you go. That may be better than mine. Maybe do I need to steal this one? They do the lagging up and the leading down, but it's showing, how power, it can move either direction. So anyway. All right. Oh, let me see if I can, I think I can find that bill. I just need to search my email real quick. Let's see. Michelle Davis. Compressed air. Screening report. Here we go. Example electrical bill, that's what I'm looking for. This is it. So this is the real McCoy right here. If you know anybody that works for these people, don't tell them. I'm showing you their corporate documents. I don't think they'd really care, but anyway. So this is what comes in. This is a kind of summary, but here's where the rubber meets the road. Okay. On peak metered kilowatt hour, 469.22. Off peak metered kWh, 1,971,000. So then their total kilowatt hours would be the sum of those, right? Okay. Interruptible, they're not on an interruptible. An interruptible rate is one. Tennessee Tech's on an interruptible rate. You can contract a certain amount of your load or all of your load that they will call an interruption when demand goes really high on the grid, and you have 5 or 30 or 60 minutes to reduce your load by that amount. And you get a discount every month for doing that. It's called an interruptible rate. Tennessee Tech's whole campus is on interruptible because we have diesel generators down here that we can fire up. and pray that they start when they try to fire them up, because they don't always. But sometimes they do. But anyway, we get I think it's $250,000 a year discount on our power bill by having those diesel generators. Firm contract demand 5,000. That's on peak, and firm off peak 5,000. Metered, see, look, their metered demand was almost the same. On peak was 39.38. Off peak was 39.52. And look, their leading kVAR. This is, I believe, at the point of minimum load, at minimum demand, and the lagging is at maximum. And here they're remembering for the past 12 months. So the worst they've done is 41.92 in the last 12 months. So that's the ratchet. They're just showing you right there. Okay. So determination of current on-peak build demand. So they're taking the higher of the metered, or they've got this algorithm, 30% of the first 5,000 kW plus 40% over. And so when they do that calculation, they get 1,500, and they go, crap, I'm not going to charge them for 1,500 when I can charge them for 39.38. So they're going to pick 39.38, and you would too. All right, so that's your on-peak billing demand. Off-peak, so here's the off-peak ratchet. So the off-peak has been a little bit higher, 42.02. And now they're doing the off-peak billing demand, so it's the same thing. And so it turns out to just be the metered demand. Most of the time it's the metered demand. So it's 39.52. And now they're picking the biggest of these to be the maximum demand, which obviously 39.52 is a little bit bigger than 39.38. Okay, so here we go, team. Customer charge, $1,500. Thank you. Administrative charge, $350. Thank you very much. Okay, on-peak energy. So that was the on-peak right there. 460,922, 460,922 times this point, this is better, 0.03364, 15,505. Okay? Here's that first block. So we got to do all that math now. We got to take, what was it? It's the on-peak. So it's the on-peak demand. It's 39.38 times 200 times the ratio of this energy divided by the total energy. So then you got to add them both together. You do all that math, and I checked this one time. It's correct. That comes out to 631,960 kilowatt hours. Okay? So this is the off-peak energy. So that first block is the same. So that's 21,000. Then the arithmetic is the same on the block size. So it's 631,960. And see, you look up here and you go, well, I got to pay for 1.87 million. So I haven't, you know, I got to pay for all the first block, all the second block, and I got to pay for the rest of them in the third block. Okay. So the cost goes down. Look how the cost goes down. Yeah, look at this one. So this second block is 0.0031. So we go from, for the same number of kilowatt hours, we go from $21,259 to $1,959. Dadgum, that's almost $20,000 less. And in the third block, after you add those two together and subtract from that total, it leaves 607,000, and that's 0.00055. That's only $334. Now, would it make sense to shift some of this? Because if you can get it in that off-peak, it'll go down to this third block. Holy moly. Mildred, we're just going to have to get you working the midnight shift. It's too much money. We'll give you a $500 a month bonus, Mildred. There you go. We'll boost your salary if you'll work the third shift. Something to think about. All right, and then there's a facility rental, and there's that 1552 times $1.46. They do have a credit, which we're out of time. But so their bill was a cool $125,000 a month. Woo! Takes money to make money. All right, guys, y'all have a great weekend. I'll see you next time.